Thank you very much. Thank you for the organisers for the invitation. I'd like to start with a couple of general remarks, because I have been to most of the free boundary conferences, which the first one actually happened in my University of Oxford back in 1974, and then there was another one in Gatlinburg in Tennessee, is it?
Yes.
In 1977, and one in Durham, run by the London Mathematical Society in 1978. And it was the kind of culmination of these activities which led to the one in Montecatini, run by Mario Primicero and Antonio Fasano in 1981. So this sequence has been going on for quite a long time. However, I feel very sorry that this is the first time in the series that we've had parallel sessions. Now, I always thought free boundary problems was a lovely area because it brought together people from lots of different disciplines: theoretical, applied, experimental, numerical, analytical. But everybody was interested in everybody else's work, so everybody could hear what everybody was doing. And I feel particularly sensitive about this because I would much rather be hearing the talk in the other room than what I'm saying now. The door's that way, Charlie. Anyway, what I would like to do is quickly tell you about a couple of free boundary problems that have bothered me in recent years, both involving high Reynolds number fluid flow. For those, one or two of the organisers were worried about my title with an RE in it. I think they thought it was high real number. Real number fluid flow? Real part of something? I don't know. Anyway, RE stands for Reynolds number, which measures the sort of inertia forces in a fluid compared to the viscosity. And if it's large, then the viscosity effects are mostly quite small. And I'm just going to tell you about two such flows. Everything else is going to be ignored apart from fluid inertia and a little tiny bit about the viscosity. The first one, which already seems to have gone wrong here because, yes, that's what it should be. It's me and my colleagues Ian Hewitt and Tom Witelski, who's already been mentioned, I think, today, and Nick Hall-Taylor, who is an aging chemical engineer who posed the problem. And this problem arose in connection with two-phase flow in pipes. So I've drawn a typical pipe there, and I've drawn some blue water and some green air going through that pipe. Such devices occur all over the place whenever you're doing heat and mass transfer, in the food industry, in the oil industry, and in particular in the nuclear industry. If you're interested in cooling nuclear power stations, if something goes wrong, you have a lot of such pipes carrying mixtures of air and water. And it was because of the nuclear industry and the amount of investment in it in the 1960s that this particular flow configuration was observed in many situations. So this is going quite fast. The air is probably going 100 meters a second or more. The water maybe a few tens of meters a second. And in that situation, you very often find that the water sticks as an annulus around the edge of the tube, and all the air goes rushing down the middle. And there are droplets and things which can fly around, but the most of the mass flow, as far as the hot water is concerned, is in these green bumps, which after a little inlet distance up to about there, they start to form very regular wave trains. Very surprising in such a situation that you would get regular wave trains when the water is being really driven by the air rushing through. And each of these bumps is part of an annulus going around the tube, and the radius of the tube is much, much larger than the thickness of the green film or even the amplitude of the bump. So I'm just going to do a two-dimensional slice through the tube to make a mathematical model of that. And I hope you can read the sizes of the numbers there. And what is interesting is this kind of permanent wave train going along the tube is observed over orders of magnitude of inlet flow conditions. And yet there seems to be no theory for predicting how big these bumps are, what shape they are, and what their spacing is. All I can really say is that the Reynolds numbers in both the air and the liquid are large. Well, what's the simplest? If you look at a configuration like that, you might think of wind-driven waves on the ocean. Well, this isn't the ocean, it's very, very shallow. That's a few millimeters thick, that green sublayer, and the total bump is only less than a millimeter thick. You might think of wind-driven waves on cornfields, for example, where it tends to be the turbulence in the air that produces the waves you see on a cornfield. Or you may think of solitons or something like that, but none of those seem to work with this scenario. And the simplest scenario that we could think of is this picture here. I'm just moving with one of those green wave bumps so that the air is still going, rushing past me, the wind-driven air that's driving this bump. And because there's a bump, the air would inevitably separate somewhere near the top of the bump, so producing recirculating eddy there. And it turns out, although it's difficult to measure which direction, how big the flow in the liquid layer is underneath, but it's not very important. Probably there is some back liquid flow, but the main liquid flow would presumably be another vortex, a green vortex up there. So I'm going to try and make a mathematical model for that free boundary problem, which has a green free boundary and a blue dotted free boundary. Now, the moment we see high Reynolds numbers flows in 2 dimensions with closed streamlines, there's one of the few theorems in inviscid fluid dynamics, which you've probably all heard of, Prandtl and Batchelor being the professor here, once founded this place. Without him, we probably wouldn't be here. If you've never seen this theorem, first of all, be aware it isn't really a theorem. I don't think it can be proved. Well, it assumes you can prove existence of Navier-Stokes for a start, so it's not going to be a theorem. But here's a plausibility argument. If you have something like this green vortex, and you take the curl of the steady 2-dimensional Navier-Stokes equations, you get rid of the gradients, and you get this term. Sorry, is that? And so, where omega is the vorticity, the curl of the velocity u, and now if you just take the integral around, say, the outside closed streamline, call it omega, that region inside that outside green streamline, then you just get the integral of the curl of the vorticity, the line integral around the boundary of omega is 0. Now this is where the dodgiest part of the argument comes. At high Reynolds number, u is the curl of the stream function, the vector stream function. Omega is therefore 0 omega of psi. And if you were to put the Reynolds number equal to infinity there, it's very easy to show that omega just has to be a function of psi. So if you were to assume that you could put the Reynolds number infinity there and solve this equation, you would get that omega is a function of psi. You put that in there, and you get the omega d psi times the circulation around the omega is 0, and the circulation is non-zero, so the omega by d psi has to be 0. So omega has to be a constant, and that is the Prandtl-Batchelor theorem in quotes. Now, if that's the case, it obviously makes this scenario much easier to analyze, and I can write it like this. I get uniform irrotational flow coming past. There's the recirculating flow in the air, which has got an omega gas, I called it G for gas, and a recirculating flow in the liquid with an omega, which is omega L, and those are both just numbers, so they're just Poisson equations with constant right-hand sides. And I can use a velocity potential in the gas, is more convenient than the stream function. There's no compressibility in this. The Mach number is about a fifth at the most. So we have these now. We've got these 2 free boundaries still, the green and the dotted blue. We can, the other thing, the observational fact I haven't made use of is the fact that these are very shallow. I've greatly exaggerated these slopes. They're 1 in 20, the green and the blue, if the blue one exists, which we're not absolutely sure about, but we're proposing that it does. So we can use thin aerofoil theory to analyze the blue streamlines in the gas, and in each of these recirculating regions, well, the Laplacian just becomes the d2 by d the normal derivative squared, and so you can really, there obviously will be regions near the edge where you have to be a bit more careful, but I'm not going to go into that right now. So there is the flow in the gas, and it's very easy to relate the pressure because the green is barely noticeable. You can relate the pressure at the bottom of the gas flow to the slope of that green free streamline. It's the Hilbert transform, and it's a very easy problem to solve. There's the flow in the water recirculating region, which you can just solve as just an ODE, and the same in the air. And I'm not going to go through any details. It's utterly trivial high school mathematics. But if you do actually solve the green problem and the blue problem, you actually show that this bit of the green boundary can't exist, because you can't get from a dotted blue and satisfy both the dotted blue condition and the black condition at the same time. So you're inevitably forced to let L equal L prime, i.e. to make the downward slope of the green free boundary vertical. And if you recall the first slide I showed, it wasn't just my shaky pen. They do have much more vertical lee sides, these waves, than the upwind side, so that isn't such a bad result to have. Once you've got that picture, sorry, no, I'm getting lost now. There. Then you draw that middle streamline as a vertical, and you've just got to solve that Hilbert transform problem. Well, if it's periodic, I have assumed it's periodic here. I could take the period to be infinity, in which case the cot would just be a 1 over, but it's a finite Hilbert transform, and it's an equation for this free boundary. I can call it just H now, even though it is part green and part blue. And there are 4 parameters that come in from solving Bernoulli's equation in those blue and green problems I had. That's a bit of a nuisance. But fortunately, my colleague Ian Hewitt realized, well, he tried to solve this equation for various values of these 4 parameters, and he just couldn't do it unless the 2 omegas turned out to be the same, and L turned out to be halfway from 0 to 1 in the period. So that would be very nice if a mathematician could prove you only got a solution to that problem with sufficient smoothness conditions, obviously, at these 2 points and there, if those 2 numbers, those 2 omegas are the same and the p is the same. Of course, the vorticities aren't really the same in real life because you have to scale them with the density of the fluid, and the air is much less dense than the water. So the air vorticity is actually about 1,000th of the water vorticity in physical terms. But if we could solve, well, we went ahead and did it under this assumption, and we were then able to collapse a great many experimental observations of these pipe flows in a way that hadn't ever been done before. But it relied on 2 mathematical things, both of which I think need further attention. First of all, the Prandtl-Batchelor theorem, and I'm particularly happy that this was on my slide because Jim was talking about high Reynolds number turbulence. And there is increasing evidence that I've seen, I don't know how believable it really is, that if you are doing, well, it doesn't have to be even 2D, that if you concentrate on measuring vorticity in turbulent flows rather than just the velocity or the pressure, which is normally done, you do see quite a lot of evidence for blobs of constant vorticity, but not quite in the way I've got them, having them actually separated by vortex sheets along the interface between them. So there might be, you might expect a sort of Kelvin-Helmholtz instability as a result of, you see this air is rushing past 10 times faster than the water, so you might expect Kelvin-Helmholtz instabilities, but if you can jiggle around with the vorticities, you might be able to get the effects of that instability minimized. Anyway, that's my first problem. I better rush on. The second problem I want to quickly tell you about concerns bubble collapse. Now, we're all very familiar with bubbles. They seem nice benign things in your champagne glass or your beer glass or whatever, and most of the bubbles we see in such circumstances are nice spherical objects. But it is a fact that bubbles can turn very nasty on you if you subject them to reasonably mild perturbations. If you suddenly, for example, increase the pressure in the liquid in which they're sitting, forgetting about gravity for a moment. And this was first analysed by Rayleigh, who proposed the following free boundary, and I would say one of the grandfathers of all free boundary problems is the collapse of a bubble of constant pressure. It may be a vacuum, it may be the vapor of the liquid, or it may be a gas, but as long as it's constant pressure, you can model it as, and there are no other boundaries around, you have an inviscid irrotational liquid around the bubble, that is with a velocity potential, and I'm calling it phi naught for reasons that will become apparent in a minute, and it has a radius which is going to be a function of time, and I'm going to suddenly hit it with a pressure at infinity to make it get smaller. And then you have to work out what this R naught of t, what this R naught of t is in order as time evolves. And the free boundary conditions of the Bernoulli equation, expect you'll see this. One measures the pressure at infinity that you're imposing, and the fluid is at rest at infinity, and the pressure has to be zero at the bubbles. Let's assume it's a vacuum just for simplicity, and your kinematic condition and your initial conditions. Now this is a nice little problem which I remember doing when I was an undergraduate. I don't know many undergraduates today who would do it. They might, if they were lucky, get them to write down that. And solving Laplace's equation, that should have a naught in it. And then when you put it into the boundary condition, you get this beautiful equation, really beautiful second order nonlinear ODE for the radius. And I wonder how many people in this room could solve that equation explicitly. It is possible, but I usually have to get my wife to do it because I can never remember the transformation. But she can always do it. You can actually write down an explicit solution of this equation, and you get this wonderful finite time blow-up. So not only was this a paradigm free boundary problem, but it's a paradigm blow-up problem too. And it occurs all around you all the time whenever you have a spherical bubble collapsing. And you can get all the asymptotics. The radius looks like the 2/5 power of the time to blow up. There's a constant which involves the 5th root of 25 over 6, what could be nice, some beautiful sort of elliptic-like function in the formula for T star. So that's what happens when a spherically symmetric bubble collapses. And what is really fascinating is you just have to make it slightly asymmetric, not quite spherically symmetric. And if you look at an experiment or even do it on a computer, you see this kind of scenario. So here I've introduced a wall beside the bubble. I'm still going to impose a pressure at infinity. But what you tend to see is, well, the bubble starts to collapse, and if it's moving at all towards the wall, it collapses in a way where it loses symmetry by turning kidney-shaped. So it starts off spherical, and then it turns kidney-shaped. And then, in a very short space of time, that kidney develops dramatically into a jet which interpenetrates. It penetrates through this side of the bubble, goes out there, and smashes into the wall. And that can be going so fast, that jet of air or vapor, well, it better be vapor if it's going to do damage, that it can cause, well, if you ever look at a propeller blade on a ship, if it's been in use for a year or two, you will find many, many small cavities in the surface of the propeller blade, and they are all caused by bubbles. You see, propellers create a vast number of bubbles, as you can see if you're on a ship, and all these bubbles are in the vicinity of the propeller blades, and they inevitably, some of them collapse in this way. So, I found this very puzzling for a large part of my life. Why should it be that if you're starting off with a lovely smooth bubble and you increase the pressure, how can you suddenly get a jet which is powerful enough to make a cavity in a piece of steel? Where's that small parameter come from? Well, I then, after some thought, and in particular talking to John Blake in Birmingham, who's a world expert on these things, he said you've got to put some asymmetry into it. And there are various things you could do. You could give it an initial velocity, but that doesn't really affect things very much. Or you could switch on gravity, slightly, just allow for a small amount of gravity. And that, although it may not be very relevant physically, it's very nice mathematically, because the Bernoulli condition, instead of being p equals 0, now that's really gravity, that delta term there. So you just have to solve the free boundary problem I had before, but with this azimuthal variation in spherical polar coordinates. So it's an axisymmetric free boundary problem, but it's not going to collapse spherically. And I'm keeping the same spherical initial conditions. Well, if we go ahead and do that, do the normal perturbation expansion that you would expect to do. There are your perturbations to your velocity potential and the perturbation to the bubble shape, which is just a first Legendre polynomial with a coefficient b1, and you naturally get some linear equations for a1 and b1. But unfortunately they involve r0, the unperturbed solution, and again it's a case of calling on the wife to understand that, because it's a real mess. But she was able to show that as you approach the blow-up time of the spherical bubble, the perturbation to the bubble shape gets larger and larger, like that time to the minus 1/5, and something else. So C is the, I think that's something to do with what A1 does. Anyway, you can see that when tau to the minus 1/5 times delta gets to be order 1, you have to, and R gets to be tau to the 2/5 when that happens. So your bubble has shrunk down to within the 2/5 power of the time that would have blown up when it was spherical. When you rescale on you actually turns out to be, tau has to be delta to the 5/3 and R has to be delta to the 2/3 in terms of the gravity parameter. And the velocity potential is getting large, the velocities are getting large. So this is no longer going to be even remotely spherical when you get down to within that sort of time of the spherical blow-up. So what do you have to do? Well, you have to, using expansions, you have to do what you'd rescale to take everything into account, and lo and behold, you get exactly the full problem for a cavity in an arbitrary shaped bubble, axisymmetric, del squared phi is 0, with a full Bernoulli condition and the full kinematic condition. I put a minus in front of the time because I'm working with t star minus t rather than t, because that's the time to blow up. But here's the twist, and this is why I'm really pleased to be able to present this to an audience with so many good numerical people. I've got to provide initial conditions for this. Well, I know what the boundary condition is, everything's going to go to 0 and infinity, but the initial condition must be as tau goes to infinity. A real t star minus t goes to minus infinity, because I've got to match backward in space and time, and I have to match back so that it matches with what the spherical bubble was starting to do and a small perturbation to it. So I have to have, for large values of tau and R, the potential has to satisfy this dependence on tau and R and theta, and the bubble shape, and that's the spherical bubble shape, but it's got this perturbation to it as a result of the gravity, and that's that C term that I had on the previous slide. Now, I have tried this out on 1 or 2 numerical people, but nobody has really risen to the bait yet. It seems to me you ought to be able to start at, say, tau equals 10 and apply these boundary conditions that R is equal to 10 to the 2/5 or something, and see how it works. But I really don't know how that is at the moment, and it's very much a matter of ongoing research, I think. I don't even know whether this problem is... Yeah?
If you are hoping that this will describe the long term, I mean, the behavior of the
jet, yes.
Should be relatively stable. Why do you care so much about initial conditions?
Because I want it to suddenly turn into a jet, this bubble. You see, it's in nearly a spherical bubble, but it's got this cos theta perturbation, which is the beginnings of this kidney shape. And I would like to think, well, probably in finite Tor, that it would do something. My dream would be starting. So this will be my initial condition for large Tor and R, and then I might expect that it's probably going to get a bit smaller and possibly turn into something, well, until it hits there, and then obviously I'd have to reformulate it, because unless I were doing it in Lagrangian or something like that. But I would like to see that this could lead to something really violent coming and hitting there. Would be what I'd like to happen. But I don't know if those boundary initial, I don't know whether to call them boundary conditions or initial, they're matching conditions from an asymptotic point of view, whether that's a well-posed problem, and so whether it can be solved numerically. So I hope that's given you something to think about, and thank you for listening to me.
So, are there further questions?
I again go to my question because I didn't understand, okay, sorry for my ignorance. If you run numerical experiments from a configuration that is more or less typical of what you started there, are they able to see this beginning of the jet?
Well, that's what I don't know, because people they like to have initial values at time t equals naught, and some bounded condition. But I've got conditions as you go to time and in distance both going to infinity in the right 2/5 power way. And that's where the you'll have to be careful numerically, I presume. Okay?
So if you do linear stability of the sphere, is the cos theta mode the one that grows fastest?
Yes. That was another good reason for doing it. But you'd get different power, instead of 2/5, you'll get different powers if you did the next Legendre polynomial and so on. But obviously, to do a complete theory, you want to have all the modes in there. But I'm sure this cos theta one would dominate, yes. So that was very good and accurate of you, John. Thank you.
Further comments or questions?
I have a third question. Why does it look so symmetrical if it is gravity?
Well, gravity is pointing in this direction.
Oh, it's pointing.
I'm sorry. Otherwise, I'm sorry. I wanted the x. My axis was horizontal. I'm sorry. I should have made that clear.
And once you start the neck, Lagrangian coordinates will be the.
Well, I would. There aren't people who have done full numerical simulations of bubbles without doing any asymptotics who have actually gone straight through. John Blake just lets it go through. And
this is Lagrangian.
Well, they used boundary integral methods, and so they're only working on a boundary like this, and then the boundary goes goes like this. So they don't see them, and it's only one mesh point that when there's actual interpenetration, so they forget about it.
Okay, no further questions. Thanks again.